Okay, so in the last video we introduced the concept of uncertainties and making measurements with analog and digital measuring devices. Just one more thing to add about that. As far as using an analog measuring device to make a measurement, the uncertainty is somewhat set by the precision of the measuring device itself, but it's also somewhat of a judgment call. Your uncertainty you should choose to be some reasonable value that you can justify based on your ability to estimate that measurement. And in some situations, it could depend on what it is you're measuring. A safe guideline to use is to basically take half of the smallest tick mark as your uncertainty. And so, for example, if you were measuring the length of something and you had millimeter tick marks, then you could start off by using an uncertainty of 0.5 millimeters or 0.05 centimeters as the uncertainty. Now, you don't necessarily have to use that because you might be able to go smaller than that, but that would be a good place to start. And remember, when we're talking about uncertainty, you're basically talking about a range of values where you're extremely confident that the true value, whatever true value means, lies between those two ranges, or within that range. Okay, so when making a measurement with an analog measuring device, your uncertainty should either come from the manufacturer, actually this is a mistake, this should be digital measuring device. When making measurement with a digital measuring device, your uncertainty should either come from the manufacturer or be plus or minus 1 in the last decimal place shown. And so some sensors or some pieces of digital equipment that you can buy actually tell you the uncertainty within the instructions themselves. Now, if you don't have that information and you can't find it on the internet somewhere, then a safe rule of thumb is always to assume plus or minus 1 in the last decimal place shown. Okay, and what I mean by that is, let's say you're looking at like a digital readout, and let's say it was, I don't know, 1.25. Okay, then you would assume that the uncertainty was plus or minus 0.01. Okay, remember with a digital measuring device, that last decimal, you don't have to make an estimate with a digital measuring device, but the last decimal is uncertain. And so a good rule of thumb, if you don't have more specific information from the manufacturer, is to assume plus or minus 1 in the last decimal place. If this had been, 1.3, then you could assume an uncertainty of plus or minus 0.1. Okay, so again, plus or minus 1 in the last decimal place. And finally, when making measurements involving a time measurement, you should also take into account human reaction time. Now, human reaction time, depending on what it is you're measuring, can range anywhere from 0.1 seconds to 0.3 seconds, depending on the reflexes of the person making the measurement and what exactly it is that you're measuring. Okay, so just because you're using a stopwatch that has 2 decimal places doesn't necessarily mean that there's not also uncertainty because of human reaction time in using that stopwatch. Okay, so just keep those things in mind. I'm going to do some examples of making measurements with different measuring devices and choosing reasonable uncertainties. And again, for the purposes of the IB exam, on the IA that you write your senior year, you can choose, for the most part, any reasonable uncertainty that you want, and as long as you justify it with an explanation in your report, and as long as it's reasonable, then they will accept that. Okay, so let's do an example. So first of all, is this an analog or digital measuring device? Well, this is an analog measuring device. There's no digital readout telling us what the temperature is. If I want to find the temperature, I have to look in this little space right here. And notice if I'm trying to make a reading and tell what temperature this is, all I really know is that it appears to be somewhere between 70 and 80. Okay, so the second part of this question says, estimate the temperature shown on the thermostat to the right along with an appropriate uncertainty. Now, because this is an analog measuring device, I should start by writing down the digits that I'm certain about, and really the only thing I'm certain about is the 7. Okay, and then because it's an analog measuring device, I want to estimate on the last digit. Okay, now when I look at this, I'm going to say 72 degrees Fahrenheit. With the understanding that that 2 is uncertain. Okay, because I am uncertain about a number in the ones place, that means my uncertainty should also be a number in the ones place. Okay, so if I were for example, to say plus or minus like 0.1 degrees, that wouldn't make any sense. Okay, and the reason that wouldn't make any sense is because I'm already uncertain about this 2, which has no decimals. It doesn't make sense to like tack on decimals in my uncertainty because I'm already not sure about the 2, much less something in the first decimal place. Okay, so a reasonable uncertainty should be in the ones place, and I would say that if this is 70 and this is 80, I could be reasonably confident, just kind of looking at this, that the temperatures may be within, I don't know, 3 to 4 degrees of whatever I say. Okay, so I would say 72 plus or minus 3 degrees Fahrenheit. Now, if you chose plus or minus 4 degrees Fahrenheit, does that mean you're wrong? No, not necessarily. Of course, you want to try to make the uncertainty as small as possible if you're writing a paper, but there's more than one correct way to deal with uncertainties, and it's really up to you doing the experiment and choosing reasonable uncertainties. Now, what if you said plus or minus 1? Well, plus or minus 1 basically means that the actual temperature is between 71 and 73 degrees. And I cannot say with complete confidence that that's correct. I mean, it could be correct. It's very possible. But I don't know if I could guarantee it. I might be able to go as low as plus or minus 2 degrees. If I said plus or minus 2 degrees, I'm basically guaranteeing that the actual temperature is somewhere between 70 and 74 degrees. Okay, and that's if I said plus or minus 2 degrees. That I might feel okay with. And so, if I had chosen plus or minus 2, then that would also be okay, as long as I can kind of justify, and as long as it's some reasonable uncertainty, okay? So, reasonable uncertainties in this situation might be plus or minus 2, plus or minus 3, plus or minus 4. They wouldn't be like plus or minus 10 degrees, and they wouldn't be plus or minus like 0.5 degrees, because again, we're already uncertain about a number in the ones place. We shouldn't be adding decimals in with it. Okay, so pause there, and if you need to take a closer look at that. Okay, so let's look at another measuring device. Okay, so is this an analog or digital measuring device? All right, so this is definitely a digital measuring device. We can see the digital readout right here. This bottom number that's big right here, this is the actual measured temperature, and then the top number is the temperature that you set it to. Okay, so in this case it's set to 76, and it also happens to be 76 inside. So this is a digital measuring device, and it says estimate the temperature shown, but because it's a digital measuring device, we don't need to make an estimate. We can just write down 76 degrees Fahrenheit. Now, what would a reasonable uncertainty be? Well, I could go on the Honeywell home website and look up what is the uncertainty in this digital thermostat if I wanted to. But if I don't want to do that, because it's digital, I can assume that's plus or minus 1 in the last decimal place. And in this case, there are no decimal places, so that would be plus or minus 1 degree Fahrenheit. And again, if I were to look up on Honeywell's website, I could probably find another uncertainty. It might be plus or minus 1% or plus or minus 2%. But if you don't know, then you can always go with plus or minus 1 in the last decimal place if it's a digital measuring device. Okay, so just a few more quick examples. Okay, is this an analog or digital measuring device? Well, this is an analog measuring device. This is a bathroom scale, an old bathroom scale, and it's analog, which means if we want to make a measurement, we are going to have to make an estimate on the last number that's uncertain. Okay, so I'm going to start by writing down what is certain, and let's see if you can write down a reasonable estimate here. Okay, what would be a reasonable estimate for this weight? Alright, so I'm going to write down what is certain. I know for sure it's between 190 and 200. Okay, so I can write down 1 and 9 pretty confidently. I also see it appears to be, to my eyes, very close to that fourth line, but I can't be too sure. It might be a little bit before the line. Okay, so that's 1, 2, 3. maybe 4, but I'm not sure. And so I would say 193. I would feel okay with writing down 193, and then I'm going to estimate because I'm not sure on that last little bit right there because it's really, really close. I might say 193.9, and then what would a reasonable uncertainty be? Well, so let's see. I would say that I can probably measure that to within half of a pound. And remember, with an analog measuring device, it's always a good, safe rule of thumb to go with half of the smallest tick mark. So here, each of the tick marks is a pound. So if I went with half a pound, that would be considered safe. Okay, so I could write down plus or minus 0.5 pounds just like this, LBS for pounds. Okay, that means I'm guaranteeing that it's somewhere between 193.4 and 194.4 pounds. Now, could I do better than that? Probably a little bit. I might be able to go down to 0.4, possibly 0.3, but again, with an analog measuring device, a safe place to start is always half of the smallest tick mark. Okay, now, there's always somebody out there who says, wait, isn't it exactly on the 4 line? Shouldn't it just be like 194 exactly? Well, if you think it's exactly on there, that still doesn't change the fact that you're not quite sure about that. You still have to make an estimate. So just because you think it's right on the line does not mean that you can ignore the fact that you're supposed to be making an estimate. Okay, so even if you did think it was 194, you would write down 194. You would write down 194.0, and then you would add in a reasonable uncertainty. Okay, so again, I'm going to go with plus or minus 0.5. On another day, I might go plus or minus 0.3 or 0.4. I could probably get away with that. Probably wouldn't feel too safe going too much slower than that, because then if your uncertainty range becomes too small, you run the risk of the true value not being in that range. Okay, so I'm going to erase this. And just to show you one more example, this is a digital measuring device. Remember, with a digital measuring device, we don't really have to make an estimation. We can just write down the actual measurement. And if we don't know any better from the manufacturer, then we can assume that the uncertainty is plus or minus 1 in the last decimal place. And so I would say, because there's one decimal place right here, I would say plus or minus 0.1 pounds would be a reasonable uncertainty. Okay, so moving on. Now, when you're making measurements, there's different types of what we call errors. Okay, and the first one we're going to talk about is what's called random errors. Okay, so pause it here and add this to your notes. Okay, so a common misconception is that people think that when we talk about errors in the situation, we're talking about mistakes. Okay, so just to be clear, we're not talking about mistakes by the person doing the experiment. We're talking about fluctuations in the results, so to speak. So this is not a human error type of thing. This is more things where you get answers that are not necessarily the correct value for whatever reason. Okay, so in the case of random errors are unpredictable and unrepeatable fluctuations in data caused by the measuring device, the observer, or environmental conditions. And the key characteristic of a random error is that random errors tend to scatter the data both higher and lower than the true value. Okay, so I can give a couple different examples. The other day when we did our warm-up question and I asked you to measure the length of the paperclip, I got a lot of different answers even though the length of the paperclip was the same on everybody's screen. Okay, so different people measuring the same thing could give different results. Just like a single person measuring the same thing over multiple days or multiple hours or whatever could perceive in such a way that you get different results. Because remember, when you're measuring, a lot of the times you're making estimations, and estimation at the end of the day is kind of like a gut feeling. Okay, so that could produce an example of a random error. Instrument resolution. How well can you read your measuring device? That could cause a random error. Again, if we take a look at the paperclip in the warm-up the other day, some people measured higher than 2.3 and some people measured lower than 2.3. And honestly, it was just as likely to be too high as it was to be too low, because the precision of the measuring device was only to 1 decimal place. You could have air pressure, temperature fluctuations when opening or closing a door. I've seen somebody measuring the temperature of a cup of water, and they're staring at the temperature probe on Logger Pro, and the last decimal point keeps fluctuating. It's 17 degrees. Now it's 16.9. Now it's 16.8. Now it's 16.9. Now it's 16.8. Okay, those types of things, those are examples of random error. They're random fluctuations that hopefully you want to get rid of by averaging your values together. Okay. Systematic errors, and again, when we talk about errors here, we're not talking about mistakes necessarily, but a systematic error is different from a random error in that systematic errors are consistent and they are repeatable errors, which result in the data always being deviated in the same way. Okay, so a systematic error could result in all of your data being too high or too low in a consistent way. These are often caused by problems with the measuring device being used. And here are some examples. Again, if you need to add this to your notes, go ahead and pause it here. We'll talk about an example of a zero offset error in just a second. But systematic errors could also be caused by defective equipment. For example, let's say you order a meter stick, and let's say your meter stick, instead of being, the space between the tick marks is supposed to be 1 millimeter, and let's say whoever manufactured it made it like 0.9 millimeters. Now you would never know if your meter stick was slightly too short just by looking at it, but that would affect every measurement that you made with that device. Okay, so defective equipment could possibly cause systematic error. Parallax error. So this is kind of difficult to explain on the computer without doing an in-person demonstration. But in chemistry, when you're measuring, let's say, the volume using a graduated cylinder, they always tell you to look at the meniscus. And there's a certain way you're supposed to look at it. You're supposed to basically get down at eye level so that your eyes are perfectly level with the meniscus so that you can measure the volume in the graduated cylinder. Okay. Parallax error is a type of error where when you look at something at an angle, it looks like a different reading. Okay, so for example, if your eyes are, I can't draw eyes, but let's say your eyes were up here looking at the meniscus, you might read a different volume than if your eyes were down here closer to level. Okay, and so that is what's called parallax error, where basically there's slight fluctuations in the way that you read data because there's like an angle between you and the measuring equipment. And potentially human error could also cause systematic error, although that's not as common. Okay, usually it has something to do with the measuring device or the way you're doing the measurement. Okay, so the only one I didn't talk about was zero offset error. Okay, so let me give you an example of that. Going back to this picture here, I took this picture the other day, and on this bathroom scale, I noticed before I even stood on the scale, I noticed something funny. Okay, I put the scale on the ground. I wasn't standing on the scale, and I looked down, and the scale reads 4 pounds. Okay, nothing is on the scale, but it's still reading 4 pounds. This is what's called a zero offset error, because the scale is supposed to be reading 0, and it is offset from 0. Okay, instead of reading 0, it was reading 4 pounds, which means that when I stood on the scale, whatever number was on the scale was 4 pounds higher than it should have been. Notice that this reading, okay, is about 190 pounds, about 194 pounds. On the digital scale, it was actually 190 pounds. Okay, and the reason for the difference is because this one had a systematic error, a zero offset error of about 4 pounds. Okay, and so after I took this picture, I had to go back to the scale. I had to adjust the knob on the back to calibrate it back to 0. So if you don't calibrate your equipment, that could possibly lead to systematic errors as well. Okay, so that is a zero offset error. That is an example of a systematic error. Now, how do you fix errors? Well, random errors are actually very, very easy to fix. Because random errors are just as likely to be too high as they are to be too low, random errors can be reduced by taking additional measurements and averaging the results together. Okay, this is why in every experiment you've ever done, you took multiple results and you did an average of the results, because if some numbers are too high and some numbers are too low, when you average them together, those two things kind of cancel each other out. Okay, so that means if you have the choice between taking 10 data points and 100 data points, more is always better because more reduces the random error. Now, more data points do not reduce systematic error, because the problem with the systematic error is it is a consistent error. And remember, in a systematic error, it's always offsetting the data in the same way. Okay, so going back to my bathroom scale example, no matter what it was I weighed on the scale, it would always be higher by 4 pounds. So even if I weighed myself 4 times, that wouldn't really change the fact that my results would be 4 pounds higher. Okay, so systematic errors are much, much, much more difficult to detect in an experiment. They're much more difficult to fix an experiment, because in lots of situations, the person doing the experiment might not even know they exist. I had a professor in college who was part of a team that spent millions of dollars developing dark matter detectors deep underground, and one of the big issues he talked about that they had was fixing the systematic errors that they were not even sure existed. Okay, so sometimes you can try to recalibrate your equipment, but depending on what it is that you're measuring, it may not be obvious whether or not you have a systematic error. Okay, so you just have to kind of analyze those step by step very carefully. Okay, so that is about random and systematic errors. In the next video, we will talk a little bit about accuracy and precision, and then we will start talking about types of uncertainty. Okay, so as always, please let me know if you have any questions, and I'll see you guys in the next video.